All right, wonderful. So I'm going to resize my window back a bit like so. I think I should go full screen. It's very strange in Zoom 5.1 because there's a whole world of problems with screen resolution. So here we're going to go. Yeah, okay, wonderful. The system's up and running. There's a little bit of remaining resolution. I've learned a trick. I click on gallery view and go back to speaker view, and all my problems just melt away. The resolution is just fine. Okay, so here we are, June 25th. Okay, quick announcement. Homework number 2 will be published tomorrow afternoon, and that will be due Wednesday. So you see, we have not fully achieved our usual cadence, so to speak. Typically, homeworks will be due Tuesdays and Fridays. That will be our usual state of affairs during the summer. But because we just started the session, we have kind of a special schedule. And most notably, homework 1 is due 2 days later than it usually would be. Right? Homework 1 would have been due Friday tomorrow, but it's due Sunday. Okay. And in a similar kind of spirit, we have this remark that homework number 2 will be due next this Wednesday of this coming week. Okay, so here's what we're going to do. We're going to conclude some topics from chapter 5. One of our big ticket items is appreciating the landscape. There's a vast landscape of functions, and a very closely related concept is the notion of an operator. So last time we talked about an operator, we defined an operator capital D. Okay, this is a useful opportunity to become very comfortable with the notion of an operator, because we're going to go into chapter 6 today. In today's lecture, we will be going into chapter 6, and that will be the main focus, right? Chapter 6, of course, is the subject of homework 2, right? So we have a responsibility here. We must talk about chapter 6. The way Taylor's book is organized is very nice. Chapter 6 is devoted to topics in pure mathematics. Then in chapter 7, we apply these principles, the calculus of variations. In chapter 7, we apply it to physics, and we talk about formulations of classical mechanics that involve variational principles, right? And you recall in a recent meeting, I showed you some slides by Andy Charman, a very interesting slide showing you that variational principles are useful even in accelerator physics, designing state-of-the-art machines, light sources, right? One speaks of, quote, light sources, really we're talking about X-rays. There is a huge user population out there. They demand ultra short bursts of X-rays, right? All kinds of fascinating science, photosynthesis, combustion science, making engines that burn fuel more efficiently, including jet engines, mapping out proteins. Lots of scientists require ultra-fast X-ray pulses, and some of the mathematical methods that are used here, the calculus of variations. So yeah, our main interest right now is getting into chapter 6 and appreciating the mathematical framework, okay? So we will be talking about various higher dimensional spaces and generalizations of our usual notion of functions, okay? So this discussion that we're gonna have right now in chapter 5, it is an opportunity to start expanding our horizons. We have this thing called capital D. It's a differential operator. If you've had quantum mechanics, you love differential operators, and you love talking about operators. Let's define this differential operator. It's actually the sum of 3 operators. The third operator is just multiplication by a constant. That's still an operator. It's okay if it's a simple operator, which is just multiplication by a constant. So this is our operator, and let's just observe. If you have a function of time you can apply this operator D, capital D, and get a new function of time. And that statement is true for each of these three terms, and it's true for the sum. So here we will apply second order time differentiation. Here we have first order time differentiation followed by multiplication by a constant. Of course, those two operators are they commute. You can change the order, but for clarity, we write it like this. Makes it abundantly clear that you differentiate the function and you multiply by a constant. And this last one, you just multiply by the constant omega naught squared. There's our differential operator. And we really want to emphasize the mathematical setting here. This is a mapping. An operator is a mapping. Okay, just like a function. And we've talked about a lot of functions. For example, when you do one-dimensional mechanics, you're interested in the position of a particle as a function of time, x of t. This is a traditional, the traditional notion of a function, x of t, the position of a particle as a function of time. It's a mapping, right? You provide some input information, the time, the function produces an output value, which is the position of the particle at that time. So the general notion is that of a mapping. And those functions x of t were a nice example of mapping. This is a mapping. The range and domain are different, right? Here, the set of allowed inputs is a set of functions of time. That's a huge, function spaces are huge. So this is a mapping from a set of functions to a set of functions. That's what this is. Later today, we're going in chapter 6. We will have some rather sophisticated mappings there. That's going to be the key to understand those mappings. So this is a nice warm-up. Let's understand this capital D differential operator, right? The differential equation in our physics notation okay, so this equation here, this is the culmination of a hierarchy of problems that we solved. We started with a simple harmonic oscillator. We started adding more physics in the sense of adding more terms here. So now we have the original, you see the original simple harmonic oscillator, this x double dot and that term there. Now we added the damping and we've added a driving force here, right? So this lowercase f, of course, has dimensions of acceleration. It was the original force divided by the mass. All right, so we're very comfortable with this differential equation. And let's observe. This differential equation has the structure now using this nice operator language, D. Okay, so we must solve this differential equation. You see the notation has become rather compact. Okay, so I've circled it there with a pencil. That's the exact same statement. We haven't changed the statement. We've just introduced some notation. Okay, but this notation enables us to organize the thinking very clearly. We're going to work out the general solution. Okay, so let's observe the structure that emerges here. The general solution is going to be accomplished in the following way. Okay, so the general solution for x, we're going to write it as the sum of two terms. There's the so-called homogeneous problem, and then there's the particular solution. So we have the x sub h plus x sub p, okay? And let's understand what these two things are. This is the solution to the homogeneous problem. All right, and this is a particular solution. Okay, and let's appreciate what's happening here. So for the homogeneous solution, you are going to solve the problem at d x equals 0. And for clarity, let's put the h here. All right, and for the particular one, you're just going to look for any solution of this problem here. So any solution d x sub p equaling f. Yes, this is the way we have organized the thinking. The crucial thing to understand is there are two free parameters here. Okay, so the homogeneous solution has two free parameters. Let's use a different writing implement, the pencil here. Two free parameters. Okay, so you see the structure that emerges. We have talked, right? We made a lot of introductory remarks here about this particular solution. This is a solution we described the attributes. Things like, we use terms like the asymptotic behavior, the steady state behavior, the long-term solution. All of those are popular terms here. So the initial conditions have died out. Here, I made this remark in pencil, right? Two free parameters. There are two free parameters in this solution to the homogeneous problem, and they allow you to satisfy the initial conditions. So again, the homogeneous problem has no driving force. It is a simple harmonic oscillator with the damping, right? There's some friction in there. And we know how to write out the solution, and we have two free parameters. They enable you to satisfy the initial conditions, the initial position, and the initial velocity, for example. So that's an overview of the structure here. So let's now talk about how we use this approach. Okay. So we're going to complexify the problem. So the remaining task here is this one. This is the remaining task. How are we going to solve this problem? It turns out it's useful to complexify the problem. It's a little bit of a paradox. Why would we intentionally make our lives more difficult? There's no need for that. Life is difficult enough as it is, right? Well, it turns out if we complexify the problem, it turns out we will actually be able to solve it with greater ease. It'll be easier to solve the problem. And the reason is we will have these complex exponential functions. So let's remind ourselves the function f of t, that function right there was an f naught sine omega t. Sorry, that was the cosine, my bad. That was the cosine. So this one had the f naught cosine. Okay, so you see, it becomes a bit of a burden when you start differentiating these things. You get these sines and cosines, it gets a little bit annoying. Life is much easier if you use complex exponentials. So we're going to introduce a new problem. So introduce a function y of t, and we'll solve this problem. So the same differential operator, this is a new function that we're going to introduce as function y. So if you apply that, for clarity, I like to put parentheses like so. This makes it clear that the symbol y by itself, that's the name of a function. And so it makes sense to talk about capital D operating on y. It gives you a new function. This object is a function, so we can apply it to the time t. Okay, so nice use of parentheses there for extra clarity. And we've got the f naught. So we got this new problem. Nobody asked us to solve this problem. Why would we create a new problem? This one here, I'll point with a pencil. This one, this is the one we're supposed to solve with the f naught cosine. That's the real problem. So the idea with this is we introduce a new problem. There's a new function y of t that we must now find that satisfies this. Okay, so the really cool thing is if you define the quantity z, so this is a new function. We're going to define z of t to be x plus iy. Okay, and now something truly wonderful happens. We can ask the question, what happens if the differential operator D is applied to this function Z? Okay, and this is great. What happens is you get F naught e to the I omega t. Okay, so this is a really good development, a really positive development. So the whole purpose here with complexifying the problem, that is, we introduce this function y of t, even though our only goal in life is to find x of t, it's useful, right? Generations of physicists have learned it's useful to introduce this function y. So now we're looking at this complex valued function z, and this is a very nice state of affairs here. Looking at this equation, we can easily solve. Remember, our remaining task is to solve for a particular solution. That means we just need to find some solution to this problem. We can do that here. We now use an ansatz. Okay. For a particular solution, so again, the subscript P is used to indicate we're looking at a particular solution. We're going to look at a constant, complex constant C e to the I omega t. And you can see we're going to meet with success here. Because if you take this function, again, C is just a constant. I'll just point like this. C is a constant. And then you have this e to the I omega t. So something wonderful is going to happen. When you apply the differential operator, second order time differentiation gives you two multiplicative factors of I omega. And there's a first order time derivative. You see, we're going to get a quadratic polynomial. Okay, so we'll skip the rest of the algebra. The important thing for us right now is to appreciate the structure and to really appreciate and have a proper understanding of this capital D. It's a differential operator. It's a mapping, okay? It's a mapping from a set of functions to a set of functions. We ask only that second order derivatives exist. They don't even have to be continuous. As long as they exist, we're happy. If you have the set of twice differentiable functions, then you can apply this differential operator to any element of that set. Okay, wonderful. So that's going to have to basically be the end of our technical discussions of chapter 5. We need to move into chapter 6. Let's just observe, if you take this ansatz here, I'm pointing with the pen, you plug it into the differential equation, you can satisfy the differential equation if this prefactor C has a very special value, right? So the upshot is C, this complex multiplier, complex coefficient, is equal to F naught Okay, and the rest is history, right? Once you have this C, right, to get what we're really interested in the physics of the problem, that's finding X as a function of time. Well, X is the real part of Z. So once you have this function Z, you just take the real part and then you've got your solution to the problem. Here, this wonderful formula here for the constant C, I'll point like so. Obviously the numerator is a real number, F naught is a real number. Downstairs, we have a couple of things. There's a real portion, omega naught squared minus omega squared, that's real. And then the 2I beta omega. Okay, so there is some bookkeeping to be done. We have to organize the thinking, identify the real and imaginary parts, etc. So that, that discussion, we're going to leave that to the reading. Remember, much of this was covered in Physics 7a and Physics 8a. So there's only so much time we can spend on it here. Okay, so we're going to move on to chapter 6. Chapter 6 is going to involve some rather sophisticated mathematics. So let's not get discouraged. Let's just keep in mind, this is pretty much the most difficult part of the course. We have to grapple with these rather advanced mathematical concepts. So without further ado, here we go, chapter 6. All right, the motivational remarks, all right? Did I not make a bunch of motivational remarks here with this capital D? Really understanding this capital D, the differential operator, okay? And understanding we're living in a much greater world now where you have spaces of functions. These are huge sets, you know, three-dimensional physical space is an infinite set of points, but it's possible to quantify and make a sensible statement that function spaces are even bigger. Function spaces are huge. All right, so here's what we're going to do in chapter 6. Okay. Again, chapter 6 is a nice, it's a self-contained chapter. It's logically distinct from chapter 7, where we use our skills from chapter 6 to formulate classical mechanics using variational principles. So chapter 6, we're going to set up the framework for the variational principles. And so let's begin by discussing a certain mapping. Let's talk about a very interesting mapping. And here's what we're going to do. Okay, so here's a two-dimensional space. We have these two axes, X and Y, and we'll even choose 2 points in this space. Here's a point number 1. So that's X1 right there. Okay, it's for the calculus of variations, it's necessary to formulate things with 2 prescribed endpoints, and we'll see the reason for that later today. But for the moment, let's just take it on faith, so to speak, that we will be interested in point number 1 here, and let's say point number 2 is over here. So that's our second point, our end point. All right, we got a really good XY diagram here. Look at this. There's the Y2. All right, so it's abundantly clear now. This is point number 1, coordinates X1, Y1. Point number 2, coordinates X2, Y2. Let's consider the set of all functions that go from point number 1 to point number 2. And it's time for a little creativity, folks. You can get crazy and put these wiggles in here like so. Or you can get boring and just do a straight line. It's kind of up to you. Let's do another one that wiggles like so. These are examples. These are functions that go from point number 1 to point number 2. All right. So again, we're interested in the set of all functions defined on this interval. The interval is X1 to X2. We don't care if they're defined or not defined outside of that interval. Doesn't matter to us. Here's the interesting mapping we're going to consider. All right, it's important that we understand that this is a mapping, and as is often the case, we will say that we view one thing as kind of given and other things as variables. We said those same words when we talked about partial differentiation. If you have a function of several variables, then when you compute a partial derivative, you view the other variables as constants and you only differentiate with respect to one of the variables. So we're going to assume that there's a certain mapping F that is given, and we're going to define the following. Here's this capital S. When we get to chapter 7 and start doing physics, we're going to talk about the classical action. Okay, but for the moment, this is just a mapping. It is defined as an integral from X1 to X2. And there's this function little f. We'll talk about little f in just a moment. Okay, so there it is. It's an interesting little formula, is it not? Very interesting. Of course, we could have created an even more general framework by allowing for higher derivatives. But it turns out for our job, which is to formulate classical mechanics using variational principles, for what we're doing, we're perfectly content just with the function y of x here, y prime of x. Remember, if you have a function of a single variable, then you can indicate the derivative just by using a prime. Not a good idea if you have multivariable functions, but if it's a function of just one variable, then this is wonderful notation. The derivative is denoted with a prime. Okay, so here's the thing. Given f, all right, and what can we say about f? F is a mapping from R3 to R. What does that mean? Okay, what that means is the following. You know, we've defined this, this is called Blackboard Bold. It is a font. If you like LaTeX, you can certainly get these Blackboard Bold, like that's a capital R with 2 vertical lines. And that's our special symbol for the real numbers. And there's the Cartesian product of R with itself 3 times, also known as R3. That's a 3-dimensional space, right? You got the X, Y, Z axes. So if you have a function little f, and we'll work through an example, right? This is rather abstract. The way we're formulating it right now, it's rather abstract. We'll go through an example, but the point is we're viewing this f here, we're viewing this as a given function. So this is going to be the same function throughout our discussion. It's some function. Once you have such a function, then you can invoke the language that we just uttered for any function y of x. And remember, that's a function defined on this interval from x1 to x2. You can insert, this is functional composition. Into the first input of f, you put y of x, then you see the comma, y prime of x, and then in some cases, we have dependence on x itself, right? So f is a function of 3 variables. You could write it as f of a comma b comma c, right? Sometimes that's useful. Let's write that here just for a little added clarity. Right. So the important thing is the function f itself does not require you to differentiate anything. F is simply a function of 3 variables. Here we've called them a, b, c. For example, f could be a squared plus b squared plus c squared. That's a cool function. Or f could be the product, a times b times c. Or f could be independent. F could be a times b. And just simply ignore c. That's still an okay function. Function can do whatever they want. They can ignore one of the inputs. They can ignore all the inputs and just be a constant. Okay, so the point is you choose some function f. Once you've chosen f, the construction here produces an integrand. The integrand, and let's indicate what is the integrand. It's everything in there except for the dx. So I use this pencil to very carefully indicate what the integrand is. The integrand is this function f with y of x inserted in its first input, y prime of x inserted in the second input, and x inserted into the third input. The resulting object, which I have encircled in pencil, is a function of x. It's a function of a single variable. Once you do this functional composition, right, and again, we're thinking of f as a given function. For any other function y of x, that's a function of a single variable, you create this construction. It's functional composition on a grand scale because you've inserted y of x here, y prime of x here, and x here. Okay. Once you do that, the thing that I have encircled in pencil is a function of x, and now you just merrily integrate it from x1 to x2. The result is a single number. So what is this mapping? We said this was a mapping. Okay, so this is a mapping. It's a mapping from the set of functions okay? So you have a set of functions, y of x, and really they need only be defined on this interval from x1 to x2. We don't care if they're defined or not defined outside of that interval, but they certainly need to be defined in here. Okay, so if you have a set of functions, again, this is an infinite set. It could be wiggly. You know, obviously there are infinitely many functions that satisfy the bill here, the requirements. So it's a mapping from this set to the real numbers, right? Because this integral, after you compute the integral, it's just a single number. It could be 5.2, right? It's just some number, okay? So this mapping S, this procedure here gives you a mapping, and again, it's a mapping from the set of functions to the real numbers. Let's work through an example, because this discussion here has been rather technical. I think we should work through a nice, clear example. So here's our nice, clear example. Let's define this capital S to be the length of the path. Right? That'll be a fun one. Okay, this is going to be great. We're going to define this function S to be the length of the path. And what the calculus of variations does, it empowers you to answer very difficult questions. So in this case, we're going to answer the question, what's the shortest path from one point to another? Well, we already know in a two-dimensional flat space, the answer is rather boring. It's just a straight line. But if you're on a curved landscape, imagine a landscape with some rolling hills, okay? Or in higher dimensional, of course, in a four-dimensional space-time, when you talk about geodesics in relativity, again, you're using variational principles. Okay, even more complicated, suppose you take a piece of wire, you bend it into a funny shaped loop. It could be a circular loop, or it could be some really funny shaped loop. And then you dunk it into soapy water, you pull it out, and now you have this nice soap film with a very interesting shape, okay? The film, because of the surface tension, it remarkably has found a surface that minimizes the area. That is a wonderful calculus problem. And the calculus of variations empowers you to solve problems like that. Again, take a funny shaped loop of wire, dunk it in soapy water, pull it out, and you have some interesting curvy surface. The soap film is a surface that has minimized the area. Wonderful stuff. So in general, these problems of minimizing something like the area, they can get rather complicated. What we'll do here for this example, we'll have S be the length of the curve. So let's look back at our picture. Here's our picture. For any function y of x, you draw this picture, and then you compute the length of the curve. Well, how are we going to compute the length of the curve? We'll look at a differential installment, right? We look at a differential installment. Okay. Capital S. Let's be very clear. I'm going to make an effort, and I think I did a good job here. This is a capital S. It's very common to use lowercase s for arc length. So we have to be careful with our capital S's and our lowercase s's. So here we go, lowercase s. Here's a ds. That's a lowercase s. And again, little s is used for arc length, the length measured along the curve. So if you have a bicycle with a trip counter, you know, you can just follow this interesting path and see what the trip counter says. ds is the square root. I'll put parentheses for clarity. It's dx, the differential x, then you square that. And here's a dy, and then you square that. Right, always good to be as clear as possible. Let's factor out a dx. Okay, wonderful. So here's what we have. We have an example where this f of y, this is the notation, the way we do this in chapter 6. In chapter 7, we're going to change notation. Okay, it's the square root of 1 plus y prime squared. Okay, so let's compare here with our general framework. Yeah, and you see here in the upper right, I remarked the function f is a function that takes 3 inputs, and I'm pointing with the pen here in the upper right. So you could think of this as f of a comma b comma c. You don't have to plug in derivatives. You can plug in whatever you want, just 3 different numbers, right? But the notation that's used in the book is looking ahead to the idea that we're going to plug in y, y prime, and x. This will be our standard template. We're always going to be interested in plugging in y, y prime, and x. And notice this function, in this example, this function is independent it is independent of the first and third inputs. That's okay. It's perfectly okay for a function to be independent of an input. And we mentioned the constants, right? A constant function is still a perfectly good function. It wants to be constant. That's what it likes to do. So it's constant. A constant function is independent of all the inputs. This particular example here with the arc length, it only depends on the second input, and that's okay. So I'm pointing here like so. It only depends on the second input. Okay, so you see now we have a framework. We have a well-defined problem. Okay, let me position the paper like this. Yep, because remember when we first introduced this stuff, it was rather technical, a bunch of technical mumbo jumbo, and it's useful to have a clear example. So we're going to go through the calculus of variations, and we're going to prove that for this function little f, the solution can be stated verbally. You're going to want a straight line path from point number 1 to point number 2. That's going to be the shortest path from point number 1 to point number 2. So that's perhaps a trivial observation here for a two-dimensional Euclidean space. But again, you can talk about much more complicated problems. You can suppose you have a rolling landscape with hills and things like that, and try and find the shortest path between 2 points. It's actually much more difficult. It's useful for airlines, right? They need to fly a plane from one city to another city. And as you know, if you fly from the West Coast of the United States over to Europe, for example, you fly way over Canada. You look out the window, it's all frozen down there because you're so far north. Well, that's the shortest path. Now, computing the shortest path on a sphere, turns out that's not too bad, you can do it. But the Earth is not a perfect sphere. One speaks of prolate and oblate spheroids. Okay, the Earth has some oblateness, and computing a geodesic on an oblate spheroid is actually rather difficult. So the airline industry, they don't actually use that result because there are other things that are much more important, such as the prevailing winds, right? But if you were faced with a problem of an oblate spheroid, that's a sphere and then you squash it down, squash the North and South Pole down, oblate spheroid, that's a nice problem. And it's interesting to find the shortest path between 2 points. Like if you're a little bug and you need to crawl from point A to point B, what's the shortest path? Fascinating problem. Okay, so this is the framework. Let's now see how this variational principle is equivalent to a differential equation. This is the remarkable thing. And when we get to the physics, of course, the differential equation is Newton's second law. So we have a formulation of classical mechanics, right? Newton's law, force equals mass times acceleration. It's obviously a second order differential equation because the acceleration involves second order time differentiation. So force equals mass times acceleration. That's a differential equation. We're going to work towards a variational formulation of classical mechanics. So a statement like this, okay? And so let's take a look at where we're going. We're going to get into some rather technical details here in a moment, but I think we should take a look at where we're going. And here's where we're going. There's a central result. We're going to show that two statements are equivalent. And when we get to chapter 7, that equivalency is going to be the equivalency between the Newtonian formulation of mechanics and the Lagrangian formulation, right? Newtonian formulation, you've got force equals mass times acceleration. Lagrangian, there's a variational principle involving a Lagrangian. So here, let's put it like this. So, of course, we're interested in solving this problem and proving that the shortest path is a straight line. We'll get to that, but first, we have to do due diligence. And let's talk about the big picture. Where are we going with all this stuff? So here's where we're going. We have this statement. Okay, so this okay. I'm putting together a comparison here. Okay, so this is one statement. We're going to show that this is equivalent to, okay, it might be time for a different pen here. Okay. Okay, so really, this is the summary of chapter 6, understanding this equivalency. So we have two statements. Okay, here on the left we have this box, and there's a statement here. This capital S, this integral taken along this path y of x is stationary. We'll talk about what that means in a moment. It's similar to the words we said a moment ago that you found the shortest path, but we'll be very precise about what that means. And we're going to say it's equivalent to this statement. This is a statement, and we're going to see that this is a second order differential equation. Okay, had to enlarge the box there a little bit to get that to fit. But this is crucial. This is a variational principle. Yeah, we got to put that here. Variational principle. Okay. And again, this really is the summary of chapter 6. On left, we have a variational principle. The idea is stationary, okay? The idea is you can compute this capital S for any, again, we're thinking of F as being given. For any given problem, you have some sort of F. For the example we did up here, this was our F. We'll do a lot of different examples, such as the famous Christophrone. That's an example from classical mathematics. We'll talk about that in a moment. But the point is, if you have some given lowercase f, there's that little f, then you have this mapping. Stationary, we have a question in the chat window. Yeah, I'm going to answer what it means to be stationary. Stationary, now let's do this. I'll do this with pencil. What does stationary mean? Stationary means the changes are second order in smallness. Okay, it means the change. This is one way to say it. Here's another way to say it. Let's talk about another way to say it. The first order changes are 0. Okay. So yeah, great question. I got a question in the chat window. What does stationary mean? This is the situation. If you have the correct path, so for a mechanics problem, when we get to chapter 7, we'll be doing mechanics, and there's the correct path, the actual evolution of the system as a function of time. When we get to chapter 7, we'll have position as a function of time. Right now in chapter 6 is purely mathematical. We have y of x. Y is the dependent variable, x is the independent variable. Okay, so what does stationary mean? It means that there is the first order change in capital S is 0 if you change this function. Okay, so if you have the correct function y of x, this is the solution to the problem, finding the correct function y of x. Now, if you make a small change, okay, so we're considering the correct solution. Here's the framework. Okay, so y of x is the correct solution. Y of x plus, and this is a lowercase Greek delta, delta y of x equals, this is a nearby function. Okay, so the basic idea here with this approach is our goal is to find this y of x, right? We want to find this correct solution. And here's the statement. If you have the correct solution, then you can look at any nearby function. So that would be your correct solution, y of x, plus, here's this lowercase Greek delta, y of x plus delta y of x. That's a nearby function. We just require this delta y to be 0 at the 2 endpoints. Okay, and then again, we have a set, remember we have that set of functions from point number 1 to point number 2. So this is a nearby function. You compute capital S, all right, and we'll see that delta okay, so now I'm going to get the red pen because it's this statement here. This is the really important statement. Okay, so I've used the red pen here to indicate this is the first order change. Again, I'm using the red pen. The first order change is 0. Okay, so again, this is rather technical. We're having a very abstract discussion. We're going to go through some examples that will really clarify it. Okay, now the remarkable thing is that this variational principle, right, on the left, we have a variational principle. We have this first order derivative, right? We have a variational principle. We're saying if you have the correct solution y of x, then any nearby function, if you compute s, the first order changes in s are 0. Okay, that statement, so that what's inside the box there is a statement. That statement is equivalent to this statement. Now this statement is just a differential equation. It's a little bit opaque, right? Because you have to compute some partial derivatives of the lowercase f. Then you insert, right? Remember, lowercase f was a function of 3 variables. Then you insert the function y. And now this, you see, that's an ordinary derivative. We'll talk about this quite a bit. D dx, that's an ordinary derivative because what happens here is you have that function, the little f, it's a function of several variables. You insert, after you differentiate that function with respect to y prime, that's its second Remember, y prime is the second input of the function f. So here, we take the function f, we differentiate with respect to its second input, then we insert y comma y prime comma x. The resulting object is a function of a single variable x because of the functional composition. Therefore, the correct notation is, this is an ordinary d. This is an ordinary derivative because of the functional composition. You compute that derivative. In the process, you will encounter second order derivatives of y. That's why this thing in the box, we're going to see this is a second order differential equation. Okay. And again, that's the summary of chapter 6. The variational principle is here on the left, and we're going to show the variational principle is equivalent to this differential equation. So when we get to chapter 7, we'll have the Lagrangian formulation of mechanics here, and we'll have good old force equals mass times acceleration, a differential equation here. Okay, so let's start working through some examples to see how this works. Okay. So let's complete the example that we had up here. Remember, and I think what we're going to do is actually squeeze it in. Okay, here we go. For this example, we were interested in the length of the path. Okay, here is our function lowercase f. Let's look at what we have to do. We have to compute the partial derivative of f with respect to y. So the really important thing here is to understand that y prime, and x are independent variables. And this must be emphasized. These three variables okay, and you know, I've taught this course 11 times. I can tell you this is one of the most confusing things about the course. From the perspective of this function, we must consider these three inputs as independent variables. And remember earlier, it is useful to think, when you think of the existence of this function lowercase f, think of it as lowercase f of a comma b comma c. Okay, these are three independent variables. If you want to make a connection with the physics, then here's the crucial thing. The classical state of a system, suppose you have a particle moving in a one-dimensional space. The classical state of the system is given by the position and the velocity. Remember, and those are two independent quantities. When you launch a particle, when you begin an experiment, you can choose the position and the velocity of a particle independently. Okay, so it is in that context that we speak of the independence. The position and the velocity are two independent variables if you have a single point in time. Okay. Of course, later when you solve the problem, you'll have some formula for the position as a function of time, x of t. And then you simply differentiate that to get the velocity as a function of time. So as functions of time, the velocity as a function of time is the derivative of the position as a function of time. Okay, that's the source of confusion. But for a single instant, when you begin an experiment, at that instant, you can independently choose the position and velocity of the particle. So it is in that sense, here in this discussion, we are thinking of y prime, and x. Okay, later when we do mechanics, this x is going to be the time t, and this is the position and the velocity. These are three independent numbers, and that's why we have these partial derivatives. Okay, so let's get right to work. The partial of f with respect to y is 0. Right? For this example, again, this is for our example, there's the function f. There's no occurrence of y here. We do have y prime, but there's no occurrence of y, so this is 0. Another thing to note, the partial of f with respect to x is 0. There's no x here. Later, when we construct the integral, you have a functional composition, y of x, y prime of x, comma x. That's later when you have this construction in this functional composition. But at this stage, the function f itself is a function of 3 independent variables, and this is it. So finally, there's one more derivative. Let's compute the derivative with respect to the second argument, the partial of f with respect to y prime. Right, so again, this is kind of the notational low point of the course because it's so confusing. This is what causes a lot of confusion. We're differentiating f with respect to y prime. That's a little bit weird, but understand y prime is just the name of the second variable. So going back to this remark here, it would be as if we were computing partial f, partial b. Right? You see, these are just names. A, B, C, those are names for the 3 inputs. So partial f, partial b. That's the derivative of f with respect to its second function. In mathematics, they have a nice notation. So rather than writing the partial derivative of f with respect to y prime, they have the so-called D2. They'll just say, we're computing the partial derivative of this function with respect to its second argument. There's no need to give the argument a name, and calling it y prime actually confuses the picture. So what is that? Well, we have the square root, right? So it's something to the 1/2 power. We have the 1/2, because it's something to the 1/2 power. Then it's that something to the minus 1/2 power. So we have a reciprocal of a square root. And then the chain rule tells us to differentiate this object with respect to y prime. That's a 2y prime. Okay, so sorry about the small font there, but this is a nice example. We know the answer is going to be a straight line, but it's useful to go through the motion and compute the 3 partial derivatives. 2 of the partial derivatives are 0 because those variables simply do not occur here in this particular formula. We do have a dependence on y prime, so we get this interesting result here. Okay, so now let's look at our differential equation. We have the following statement: partial of f with respect to y, well, that's 0, okay? So now we have this statement that d dx of this thing equals 0. So it must be true that the partial derivative of f with respect to y prime is a constant, right? Because in our case, this partial f partial y was 0. This is it's called a total derivative in the language of the calculus of variations. This derivative of this thing is 0. Therefore, partial f partial y prime must be constant. Well, look at the formula. It's just a function. Okay, I see there's a question in the chat window. Just a moment here. Partial f partial y is constant. So the conclusion is that y prime is a constant. It's a different constant. Y prime equals a constant. And so we've proven that the solution is a straight line, right? If y prime is a constant, then the solution is a straight line. So let me put a box, and then I have a question in the chat window. And it's really cool. The question has partial derivatives with the notation for partial derivatives. So why is partial f partial x equals 0? And that's a great question. And the crucial thing here is for this part of the calculation, the function f is viewed as a function of 3 independent variables. So these are independent variables. And in terms of physics, let's make a connection with our physical intuition. At a single point in time, you can independently choose the position and velocity. So position, velocity, and time. You could start the experiment at t equals 17 seconds. So that's going to be the role of this variable x. So you can choose an arbitrary value of x, and you can choose an arbitrary value for the function and the slope of the function. So these 3 numbers, at a given point, these are independent variables. So therefore, what we must do when we look at this formula, we must look for occurrences of x, y, and y prime. And those are thought of as independent variables here. That's the crucial thing. So later when we solve the problem, when you get the solution, so let's record that here. I'll move the paper. So this is a differential equation. The solution, I'll make a remark here. The solution okay. So the solution is y of x. And when you have the solution, so after you solve the problem, this is the crucial thing. After you solve the problem, okay? So I will underline this. I really want to emphasize, after you solve the problem, then y prime is dy dx. Okay, so at that point, you have y as a function of x. Once you have this function, y of x, then y prime is simply the derivative of this y of x. Okay, so that's the main source of confusion here. And so let's go through another example. The more examples we do, the greater the clarity that we'll have. Okay, so let's do the example of the Christophrone. It's so I understand that this is confusing, but let's work through some examples, and I think as we bring together some experience with this, it will become clear. Okay, so here's an example. Okay, so here's another example. This has a fancy Greek name because people have been studying this for hundreds of years. Okay, so we're going to solve the problem. And this is a wonderful physics problem, and it's actually challenging to solve. If you're going to design a roller coaster, okay, so think of a roller coaster at an amusement park, and let's do a simplified roller coaster where there's just one car, not a long chain of cars. That's actually more complicated. Let's just think of a single car, and we'll think of it as a single point. How would you design this roller coaster so that the car very quickly goes from one point to another point? If you design the roller coaster just to have a constant slope, that's a pretty good solution. It's not the best solution, but yeah, the car will quickly go from one point to another. But it turns out you can get there faster if you make it steeper at the beginning, even though you're going to have a longer path. But it's still faster to have it be steep at the beginning. You gather speed at the beginning, and then you level out. So we'll do some pictures. So possible, here we'll have possible functions. Okay, so we're going to design a roller coaster. Our goal is to get from here to here. If you choose a straight line, this is kind of, we'll put okay, it's not great. Here's one, this is a really bad idea. Okay, so let's look at this and understand this is a bad idea. If you start here, and if you start with a very shallow slope and then go like so, this is bad. Right? And again, we're discussing a roller coaster. Okay, so what will happen is the roller coaster goes very, very slowly here. You're just wasting time. It's going so slow. And then suddenly we have this drop. This will be quick, sure. But the point is, it takes a long time. So it takes a long time. Okay, and let's talk about the solution. The solution is the Christophrone. It's a very special curve. It curves down like so. And this has the least time. Okay, so so I've drawn these pictures just to bring in our experience. Again, our goal, we have these 2 points, And of course, there's gravity, right? We have gravity like so. We like to use this notation of G. The symbol is G with the arrow. That's the acceleration due to gravity. And here I've put the arrow. So this is the side view of a roller coaster. Okay, side view of a roller coaster. And you're faced with designing a roller coaster where, let's just, as an assumption, say the car will start at rest. It's actually different if there's an initial velocity. Okay, so that the constant slope, this is kind of okay, not great. You'll get from here to there pretty quickly. Okay, this is a terrible idea because you go slowly for a long time. You waste about 60 seconds. That's just a sample number. Extraordinarily slow, and then it goes like so. This is the best answer. Notice it's longer. Even though the path is longer, this is still faster. And when we say faster, that's in the sense of total elapsed time. Okay, so the crucial thing is these are all possible functions. Right? These are 3 examples out of an infinite set of functions. For any one of these examples, we can compute how long it takes to get from here to there. It would be especially easy for this one here, right? Because this is something we've been doing since high school. You know the acceleration will be a constant. Then there's just a little bit of bookkeeping to figure out how long it takes. If you have constant acceleration, you start here. How long does it take to get here? You can compute how long it takes, okay? These are more complicated. You could imagine piecewise constant paths. That's okay. We can compute the answer easily. But let's set up an integral. So our first order of business is to set up the integral for the Christophrone. Okay, so now there's just one more thing to be said. These diagrams are intended to make a connection with our experience, okay? So these diagrams relate to our experience. Okay, so now we're going to solve the problem. We're going to solve it the way it is solved in the book, okay? And so the book has the y-axis pointing down. You know from mechanics, right? First year mechanics, it doesn't matter. You choose the y-axis, have it point up, point down, doesn't matter, as long as you're consistent. Okay, so what I'll do is I'll draw a big horizontal line here. Let's now solve this the way it's solved in the book. And in the book, we have the y-axis pointing down. This is useful so we can start at the origin. Okay. So we're going to start at the origin because we have to do a very detailed calculation now. So let's set up a framework that is easy to work with. We'll have the x-axis like so, the y-axis like so. Okay, so again, that's the framework for the problem. Now, we're assuming we start here and we're going to go over to here. So this is point number 1 and this is point number 2. And now capital S is going to equal the elapsed time okay, and we would like to write down an integral. If I tell you the path here, how can we write down an integral that tells us the total elapsed time? Okay, the great news is we have conservation of energy. So conservation of energy you can solve and you get the speed, v, is the square root of 2gy. Okay, so obviously if you square both sides and divide by 2 and multiply through by the mass, this is just saying that the kinetic energy, right, the kinetic energy is 0 here. We're starting from rest at point number 1. The kinetic energy at any point on this path is 1/2 mv squared, and it must equal mgy. With y positive like so, it works out perfectly. So mgy, that's the gravitational potential energy that is converted into kinetic energy. So the good news here is we know the speed at any point in this diagram, regardless of the curve that you choose for this roller coaster, we know the speed at any location is simply the square root of y together with a constant. That's a nice result. Okay, so we can compute the time going from 1 to 2. Okay, so the time how long does it take the roller coaster to go from point number 1 to point number 2? It's equal to, there's a certain constant. We're going to see that doesn't really matter here because we want to minimize the time. Okay, so we pulled out the constant. We're going to integrate from 0 to y2. Okay, and we've got the square root of 1 plus x prime squared over the square root of y. Okay, so let's talk about this. Unfortunately, there is a role reversal. Okay, I'm following the textbook because I want to have clarity on what the textbook does, but let's emphasize that here. We have a role reversal. Okay. So this is kind of unfortunate because the subject was already confusing and now it's even more confusing because we're exchanging the roles of x and y. Now y is the independent variable. According to the framework we just set up, x was the independent variable. So the upshot is, in this discussion, we're going to talk about f of x comma x prime comma y. And now you can read it off here. We're going to throw away this constant. It's simply a constant. We want to minimize the time. That's achieved by minimizing this integral. And so our function okay, so this is a famous problem. Again, the problem of designing a roller coaster so that you get from one point to another point as quickly as possible. I use the red pen here to emphasize this is our result. We do have the role reversal, and I want to address this because this is the way it's presented in the book and we have to grapple with that. So it's another layer of confusion. Earlier, we were looking for functions y of x. Now we are looking for, so we want to solve for x as a function of y. Okay, so that's a little bit, okay, yeah, great question. We have a question in the chat window. Let's explain where this integral came from. The crucial thing here is we're basically integrating dt. Okay, so the idea is we're going to travel from point number 1 to point number 2. We'll break this journey up into differential installments, and for each differential installment, let's figure out how long it takes. Okay, so let's do this. Here's a differential installment. Okay, so we have a dy on the y-axis. If that's dy on the y-axis, then we're going to take a differential step along our journey. I've marked these 2 points on the curve. They're very close together. That's our differential step. The question is, what is dt? What is dt for that differential step? Well, dt, it's a question of distance equals rate times time, good old rate times time, right? So the time is equal to the distance traveled, right? And so this is equal to the distance, and we like to use lowercase s. Remember, lowercase s for distance along the arc. Lowercase s is a very popular symbol for arc length. So ds over v. Okay, so the differential amount of time to take this journey from that point to the neighboring point is equal to the length. We must now compute the length of this path. So that ds is the square root of dx squared plus dy squared. Okay, so there's our differential journey. ds is the square root of dx squared plus dy squared. Now we're going to factor out the dy. Okay, so this, you see, is equal to you see how it's dy times 1 plus x prime squared. So this is the integral from 0 to y2. And if you put the dy back into the square root, this is the square root of dx squared plus dy squared over root y. Yep, so great question. The question in the chat window was, where did this integral come from? And the crucial thing is here, it's the differential time is that ds, that's a scalar. That's not a vector, it's a scalar. The lowercase s is arc length. So what's the length of that little diagonal portion? The length of the diagonal portion is the square root of dx squared plus dy squared over v. And again, v can be gotten apart from a constant, it's just the square root of y. Okay, so the structure that emerges was this thing here, and we factored out the dy. Because of the role reversal, we want to write this as an integral of dy. So we'll go through this problem again with the original role, where originally we had y comma y prime comma x. It's possible to revisit the problem with that notation. Okay, so now we have this function f, and now we have a clear prescription. Remember, the central result of chapter 6 is that this variational principle is equivalent to this differential equation. And this is a clear prescription. It's a clear prescription. You compute some derivatives, then the final step, the amazing step, is this derivative. Okay, so I got another question here in the chat window. Let me read this question. Is it generally reasonable to start with our differential distance formula and determine what to pull out? Yep, that's right. So yeah, that is a good point. We had, this was a very general object that occurs quite a bit, this ds. Now in this case, we pulled out the y, and I'm reading the question in the chat window. The force is in the y direction. Yeah, it's because we have this y dependence here. This was convenience, but we're going to revisit the problem. We'll repeat this whole problem pulling out the x. Yeah, so that's a great question. And in our next meeting, because we don't have time today, in our next meeting, we'll redo this. But the point is, yes, so there's an excellent question in the chat window, which we will continue to discuss. We want to get a feeling for this procedure. Now, we must compute partial f, partial y. But remember, we have the role reversal. So now we must compute the partial f, partial x. And we must compute a partial f, partial x prime. Okay, so that means let's look at our function. Do we see any x? And the answer is we do not see an x. There is an x prime, but that's a different variable. So this one is 0. Okay. And now we must compute this one. Okay, so we see there's a square root there. Let's compute the derivative. This y is just a constant, so that's a 1 over root y. We just copy that over. And now we must differentiate this. So there's a 1/2. We're using the chain rule. It's an object raised to the 1/2 power. So we have a multiplicative factor of 1/2. Then we have this object raised to the minus 1/2 power. So that's a 1 over the square root like so. So 1 over the square root of 1 plus x prime squared. And then we must differentiate what's inside the square root. So that's 2x prime. Okay, so we'll go through this calculation. Obviously, we got rather technical here. So in our next meeting, which is on Monday, we're going to go through this again, and we're going to revisit the problem using x as the independent variable. It's possible to solve the problem both ways. I wanted to present the solution that's in the book. Okay, wonderful. So I'm going to stop the recording here. I will stay here for more questions, but let me, and you know I have to resize the window. That's part of life for me. Okay, it just, all right.